What are the specific characteristics of a metal?
Well, there are lots, so let's focus on the one that I like the best, and that is how electrons behave in a metal. And perhaps to make it easy to understand, we contrast a metal with an insulator, which I think everyone has some feeling for what that means. Electrons pass easily through a metal, so we call this a conductor. They don't in an insulator. Insulators have their use for actually isolating things, electricity from ourselves, for example, to protect us.
So how do the electrons behave in the energy levels of a metal?
That's interesting. Let's use eggs as an example. Imagine that we have one of those large catering boxes of eggs, 24 eggs, and I have another one which is empty. So one full, one empty, and I put the empty one just above the full one. The way that the electrons behave is a bit like us moving the eggs from one part of the box to another. If the holes in the box are near the eggs, then I can relatively easily move the eggs from one part of the box to the other. So these holes represent states in the metal which are empty, and the eggs represent the electrons.
So you mentioned states. How do you explain electron states and their relevance to insulators and conductors?
Right, okay. So a state in a metal is a quantum state. Everything that happens in the material is best described by quantum mechanics. So when I'm moving the eggs from one place to another, it's under the influence of some force or an energy field, for example, temperature. So what happens at room temperature with a metal is the eggs near the edge of the box that are near the holes are continually moving in and out of the holes in a random way. Now, to contrast that with an insulator, imagine we have the same two boxes, but now the box that's full of eggs and the box that's empty are separated from each other. So somebody pulls the empty box away from me and I can't reach it any longer easily from where I'm sitting. So that, it looks like the energy states in an insulator. I have lots of electrons, but they're in a box with no holes nearby. They cannot be excited to the empty holes in the egg box because it's too far away. And that's far away not in distance, but in energy. So, for example, at room temperature, they can't reach these empty states, and therefore they don't conduct electricity.
So can this egg box analogy be used to understand semiconductors as well?
Yes. Now what we have to do is pull the box back a bit. So if the box is far away in energy, there's a large energy required to move an egg from one part of the box to the other. That's an insulator. Pull it nearer to so that there's only a little gap between the boxes, and then the energy that's available at room temperature can actually move an egg, an electron, from one part of the box to the other. And if that happens, then it behaves like a metal. And the reason we call them semiconductors is that if I now cool them down, cool a semiconductor down, at room temperature it will conduct electricity, not as well as a metal, but it will. And as I cool it down, then the energy available to move the eggs to the other box becomes smaller and smaller because the temperature is decreasing. The energy just goes with the temperature.
What's so special about the properties of a semiconductor then?
Of the three materials, then the material that is most useful for making electronic devices from is the semiconductor. And part of the reason is it's got this little gap. If we add an impurity to a metal, an impurity is just an atom that isn't the same as the metal. So, for example, we could add gold to copper in small amounts. Nothing much would happen because the electrons are plentiful and there's lots of energy states, and so they will just screen out the influence of the gold. However, adding elements to semiconductors like silicon or germanium hugely change the electronic properties in a way in which, now that we understand it, we can actually control. So that enables us to pre-design, if you like, the properties of these materials so that in combination we can make devices. When you put metals in combinations, it's very hard to make a device. They are passive elements, is what we call them, not active elements. So you can't make an amplifier out of a piece of metal, but you can out of a piece of semiconductor. Well, three.
So here's a big question. Well, how are these different materials affected by different types of fields?
Well, things that influence the energy inside the material we refer to as a field. So the types of fields we can have are thermal, temperature, electric, which we can just use a battery to put across a type of material, or magnetic fields, which we generate using coils, or permanent magnets made from iron. So these different fields all affect mainly the charge on the electron. Everything I've described to you so far is about electrons, and it's the charge that is responsible for the action that we see in all these electronic devices. That was true until about 1990, when a new field of electronics was developed that uses not just the charge on the electron, but the magnetic properties of electron, which we call spin. So the buzzword now is spintronics, manipulating the spin on an electron to make it into a functional device.
So how useful are metals in reality today, and are they kind of destined for the realms of history?
Oh no, I think it could be just the opposite. Today, functionality, the ability to make electronic devices, comes by combining materials. Very few things in electronics today are one material on its own. We need to combine several materials, and the way that we do that now is on the nanoscale. So the interface between a metal and another material, like an insulator or a semiconductor, can be used to make a lot of different new types of devices. For example, a lot of materials are magnetic. Some of them are insulators, some of them are metals. If you put a heavy metal, like platinum, on top of an insulating magnet, then no current passes through the magnet. It only passes through the metal. Nevertheless, the magnetic properties of the insulator affect the current and the things that you can do with the platinum on top of the magnet. So it requires you to be able to put materials together with very, very clean interfaces.
Are silicon or graphite metal? Because I know graphite certainly conducts electricity.
It does, but not the same way a metal does. So graphite is a semiconductor, and so is silicon. So they have this gap in the egg box description. They have a space between the egg boxes. So they're not metals, no.
What about carbon fibre?
Well, carbon fibre is probably an insulator. I've never measured any carbon fibre. I've measured carbon nanotubes. They, interestingly, can behave like a metal or a semiconductor. And if you imagine rolling up a piece of paper, it depends on how the paper is twisted. So if you roll up the piece of paper such that the edges remain square, so you roll it exactly in a cylinder, then it behaves like a metal, two-dimensional metal. But if you roll it, say, from a corner so that it's more skewed, then it behaves like a semiconductor. So that's a very interesting, unique feature of carbon nanotubes. The fibers, I don't know, they're not interesting from an electronic point of view.
Well, seeing as we've discussed the other types of carbon, what about diamond?
Diamonds are a very good insulator. They have a large gap between the egg boxes, so they're a very, very good insulator. They have a lot of interesting properties. Well, you might argue that today carbon is the most interesting element in the periodic table, because carbon is graphite, it is carbon nanotubes, it is buckyballs, it is diamond, it is graphene, all of which have different electronic properties, and of course graphene today is called the wonder material. It's going to solve all our problems, according to the press.
We talked a bit about impurities, so I was wondering whether it's possible to produce gold without impurities, or whether it can be used without impurities.
You can. It just depends on how much money you want to spend and how hard you want to work. So perfect crystallinities is probably not possible. But, well, it isn't possible, is it? But in small sections, small pieces of gold, and by small I mean possibly even a few microns in square dimensions, it can be absolutely perfect. I've seen this with my own eyes in special microscopes and ways of looking at the interior materials. If you want to work hard enough to do that, then you can make it very pure. It depends on how much you want to expend. Where impurities matter the most, semiconductors, you have to be extremely careful. So the reason that most semiconductors these days are made in the Far East is because the cost of building and servicing the fabrication plants is enormous, and so costs have to be kept down wherever they can. For example, it's billions of US dollars to build a plant to make the chips that go in our phones. And if it were not for the fact that we can sell them by the billion, nobody would ever be able to afford to make semiconductors.
So is that what we see when we see those images of clean rooms where people are in those white uniforms?
Yes, completely gowned up, because anything that's in the semiconductor that isn't there deliberately is going to ruin the process.
So why are metals such as gold and silver and platinum, if you like, so valuable?
Because they're rare and because they look good on the body. So when people like to decorate themselves, they like shiny metals. Copper is just as beautiful in some people's eyes as gold, but it's much more abundant, and so it doesn't cost as much, at least until recently. In pure form, these metals are not that useful, especially gold. Pure gold is rubbish for making jewelry out of because it's too soft. So again, controlled impurities in materials is very, very important. Take steel, for example. If you don't put carbon into iron, you don't end up with steel.